The topic of today's video is the Frobenius series solution method in order to solve a second order homogeneous differential equation, right? As we discussed in the last video that when x naught is an ordinary point of a second order homogeneous differential equation, we can use that power series method, right? But we have limitations when x naught is not an ordinary point. So first I will recall that case that we did in our last video. That was if x naught is an ordinary point of differential equation, that is x square y double dash plus px y dash plus qx times y equal to 0. Let me call it equation number A, right? Then the solution to this equation number A is of the form y is equal to summation a n x to the power n, where n starts from 0 to infinity, and this is called power series method, right? But what happens when x naught is not an ordinary point? This will be the main focus of this video, right? So if x naught is not an ordinary point of equation A, right, then surely this method will not work. We have to do some modification on this power series in order to obtain the solution of this equation A, right? If x naught is not an ordinary point of A, then we say that this x naught is a singular point, right? So roughly you can say that a singular point is a point when the function blow up to infinity, like 1 over x. If you put x equal to infinity, it will go to, x equal to 0, it will go to infinity, right? So functions of this form will belong to this category, right? For such functions, x naught will be a singular point. A function having singularity at x naught will be called a singular function, and x naught will be called a singular point, right? And when I say that x naught is a singular point of these px and qx, obviously the nature of the solution of this equation number A can be similar to the nature of these px and qx. If these px and qx are analytic at some point, then we say that the solution is also analytic at that point, right? So this is the key idea. So when x naught is a singular point of px and qx, obviously px and qx are not analytic at x naught. I will write that. That is, px and qx are not analytic at x naught, right? So there are two cases after this. After having a singular point, there are two cases. If x minus x naught multiplied with px and x minus x naught whole square multiplied with qx, they become analytic, are analytic at x naught, right? Then x naught is called a regular singular point, right? So px and qx originally are not non-analytic at x naught, but when we multiply this px by x minus x naught, it becomes analytic, right? And when you multiply qx with this x minus x naught whole square, it becomes analytic. It indicates that x naught is a regular singular point, or you also call it weak singular point, right? Weak singularity, right? Weak in the sense because you can remove this singularity by just multiplying px with x minus x naught and multiplying qx with x minus x naught whole square. That's why we are saying it weak singular point, because it can be removed just by multiplying it with these polynomials, right? Okay, and if this does not happen, that is, if on multiplying with x minus x naught and x minus x naught whole square, the functions are non-analytic, then we'll say that it is an irregular singular point, right? I will write that. Otherwise, x naught is an irregular singular point. Right? It means that either of these two conditions fail, and then we'll say that x naught is an irregular singular point, right? I will give a small example for this. For example, if I consider the differential equation x square y double dash plus x y dash plus y equal to 0. Now you can see this equation has regular singular point at x equal to 0. Why? Because you can see that your coefficients are px and qx. Your px is actually 1 over x. You have to divide the whole equation by x square first, right? Because px is actually equal to how much? 1 over x. And qx is equal to 1 over x square. You can easily see that these px and qx are non-analytic at x equal to 0. If you put x equal to 0 here, it will go to infinity. Same is the case with this qx, right? Are not analytic at x equal to 0. But the good thing is that if you multiply your px with x, actually you should multiply with x minus x naught. Your x naught is equal to 0 this time, right? So that's why x minus 0 multiplied by px, that becomes 1. And if you multiply your qx with x square, it becomes 1. And you can see that both of these are constant functions, and constant function is always analytic, right? Are analytic at x equal to 0, right? Okay, so when we have a singular point, particularly regular singular point, then we have to modify this series, this power series. This power series method doesn't work in case of regular singular point, right? This works only for an ordinary point, right? So we have to do some modification in this series, and that modification, I will write that what modification should be done. So in this case, when x naught is a regular singular point, right? X naught is a regular singular point, we assume the solution of equation number A is of the form. That form is actually y is equal to, you can see here, if you see this series, if you just put n equal to 0 and 1 here, you will get a series like this: a naught plus a1 x plus a2 x square and so on, right? As I said earlier, that we have to do some modification on this series, and that modification is just multiplying this series with x to the power r, right? This r can be any real number, right? I will write that here. R is any real number, and yeah, this a naught should be not equal to 0. It is an important point. I will explain it later why a naught should not be equal to 0, right? So just by multiplying this power series by x to the power r, we get a new series, right? And this y is actually the solution of this differential equation A whenever x naught is a regular singular point, right? So this is a kind of a small modification in the power series, and that's why we called it a quasi power series, right? Or it is called Frobenius series. I will write that. This is called quasi power series or Frobenius series, right? We can also write it in summation form. If I write it in summation form, then it will become a n multiplied with x to the power n plus r, and it starts from 0 to infinity, right? Okay, and yeah, a naught is not equal to 0 and this r is any real number, right? Okay, and one more thing is there. If you have r equal to 0, if you put r equal to 0, then ultimately this series will be a power series, right? So we can say that a power series is just a special case of this Frobenius series, right? When r equal to 0. Okay, I will write that if r equal to 0, then Frobenius series becomes power series, right? And yeah, I have to tell what is the explanation behind this, why we multiplied with x to the power r, right? There is a small explanation behind it, right? And I will add that explanation for this thing. Explanation for this factor x to the power r, right? And this is very important point. Why we multiplied with x to the power r, right? So to understand this, we have to consider a differential equation having a regular singular point at x equal to x naught. Let me choose x naught equal to 0 for simplicity. So the smallest or the simplest differential equation of second order having x equal to 0 as a regular singular point is Cauchy-Euler homogeneous equation. That was the part of your syllabus in last semester, right? So I will write a Cauchy-Euler. This is also Cauchy-Euler differential equation if you watch it closely, right? A Cauchy-Euler differential equation is of type: if y double dash is present, then with this you have x square. With y dash you have x. If you have y triple dash, you should have x cubed there, right? Okay, so I will write a general second order Cauchy-Euler homogeneous equation in order to understand the presence of this x to the power r, right? Okay, so consider Cauchy-Euler equation, right? And there is x square plus small p, this is constant, right? P x plus q y, oh sorry, x square y double dash, x square y double dash and px y dash plus qy equal to 0, right? Okay, where p and q are constants, where p and q are real constants, right? So recalling that method from the last semester, what we did to solve such an equation, we put x equal to e to the power z, if I'm not wrong, put x equal to e to the power z, and this means that if you take log on both sides, you will get z equal to log x, right? And yeah, x square y double dash is replaced by d minus 1 y, and x y dash is replaced by dy, where d is the differential operator d over dz, right? And this method you already know this method, this substitution, right? And if I substitute these in my differential equation, that will become this gives, this term will become d minus 1 y, this term, second term will become p times dy, and third term will become qy equal to 0, right? And I can write it as d square minus plus p minus 1 d plus q y equal to 0, right? So you can see that a Cauchy-Euler homogeneous equation is converted into a linear differential equation with constant coefficients, because p minus 1 will be a constant, q is a constant, and now I can write the auxiliary equation for this differential equation and we'll find its roots, right? So auxiliary equation for this differential equation should be m square plus p minus 1. Should I write this equation in r, because I have r here? So r square plus p minus 1 r plus q equal to 0, right? And you can see that this is a quadratic equation. It will give two values of r. Let those values be r1 and r2. If r1 and r2 are two roots of this equation, then we have two cases when we have unequal roots and when we have equal roots, right? So I will write those R1 R2 are two roots of it. Then the solution is written in two ways. If you have R1 is not equal to R2 and when you have R1 is equal to R2, right? Okay, so when you get distinct values of R, the solution is written as e to the power what? R1 z and e to the power R2 z, right? You should remember this point. When you have distinct roots, then you write the solution as e to the power first root multiplied with this independent variable. Notice that our independent variable is z this time because we have made this substitution, right? And the second solution is e to the power R2z, right? This is the case when we get distinct roots. R1 and R2 are different. But when we have repeated roots, suppose R1 is equal to R2, let me say R, that is equal to R, say, then we write the solution as e to the power Rz, and the second solution is obtained by just multiplying the first solution with the independent variable z, right? You should remember all of those basic concepts about solving a linear differential equation with constant coefficients. When you get distinct roots, you write distinct roots m1 and m2 because you wrote m, generally you write m for an auxiliary equation. I have used the variable r. So when you have distinct roots m1 and m2, you write the solution as c1 times e to the power m1x plus c2 times e to the power m2x, where x was the independent variable, but in our case z is the independent variable. That's why I wrote this, right? And when you get repeated roots m1 equal to m2, then you write the solution as c1 multiplied by e to the power mx plus x times multiplied by c2 multiplied by e to the power m1x, right? So for in case of repeated root, you just multiply the previous solution by the independent variable x. In our case, the independent variable is z, so that's why I multiplied the previous solution with z, right? Okay, but originally I had x in my equation, z was not there, so I will rewrite it as in terms of x. So e to the power r1z, actually e to the power z is nothing but it is x, so it will become x to the power r1 and another solution will become x to the power r2, right? So this is the case when r1 is not equal to r2, right? And secondly, for this one, I can write it as x to the power r, and this will become the z, the value of z is log x, and log x times x to the power r. So this is the case when r1 is equal to r2 equal to r, say, right? So this point is very important to understand the presence of this x to the power r, right? I will come to that, but before that, we will make one important observation. Let this be equation number 1. If you see this equation, these p and q were constants, right? Okay, okay, right. And if I write the more general form of this differential equation, first I should rewrite this equation number 1. Okay, that is equation 1, rewriting this by just dividing it by x square, y double dash plus p over x y dash plus q over x square y equal to 0. I have just rewritten the equation number 1. You can see that just divided it by x square, right? That is equation number 1 has solution. Let it be equation number 2. This whole thing, this is 2. Second, has solution of the form second, right? Okay. Now what happens if I replace this p and this q by a power series? This is a constant here, but if it is not a constant, it is just a series. It means that p is a kind of function having a power series. It indicates that p and q are analytic functions. So they will be having a power series. Every analytic function has a power series. That's why if p and q are any functions, having power series, then I should replace this P by its power series. I should replace this Q by its power series, right? In general, y double dash plus the series of p naught plus p1x plus p2 x square dash dash over x, right? Y dash, and replacing q by its power series, q naught plus q1x plus q2 x square and so on over x square, and y equal to 0, right? Okay, and one more thing, if p is a constant, p may be a constant, right? Then it's all of these p1, p2 and p3 so on will be 0, right? If p is a linear polynomial, then p2, p3 and so on will be 0, right? So this is a kind of more general equation for this, right? In this case, p and q are constants, but in this case, p and q are more general in nature. They can be constant, they can be linear function, they can be quadratic polynomial, anything, right? So I am trying to write the solution for this general equation. I have already the solution of this equation of this form. So I will rewrite the solution of this general equation, right? Okay, using this. Okay. So in general, this must have solution. Must have a solution of the form. Okay, this y is equal to, you can see that. Yeah. Okay, this is, if you hide these two terms, if you ignore this x and x square, right? So you can see that this is your capital Px, this is your capital Qx. Capital Px is a polynomial kind, it's a kind of polynomial, or not a polynomial actually, it is represented by a power series, right? Qx is also represented by power series if you hide this x square, right? And then we hope that this differential equation should have a power series solution, right? A solution of kind that we discussed in our last video, where the solution is y is equal to a naught plus a1 x plus a2 x square and so on, right? If this x and x square are absent, then this equation will have a solution of this form, right? But when this x is present and here we have x square, then we always get a solution of this form. See here, x to the power r1, right? You can see this differential equation, this one. We have p over x and q over x square, right? Then in our solution, the terms were x to the power r and x to the power r, right? So that's why it is a kind of differential equation which is just formed by the clubbing of this Cauchy-Euler equation and an equation we solved in last video, right? I will tell that again, right? This part, I will write that first. This part, this solution is due to this part only, the numerator part, where you consider the denominator as 1. X is replaced by 1, x square is replaced by 1. Means we have 1 in the denominator, then it will be the solution. But what happens if the numerator is absent and the denominator is considered x and x square? You ignore the numerators and consider the denominator, then it will be this equation, right? And its solution is of this form. That's why x to the power r must appear here, right? And I'm writing the solution for this case when r1 is not equal to r2, right? And for second case, again, the solution will be multiplied with x to the power r as in this case, and another solution will be just obtained by multiplying log x with the first solution. If you see this repeated value case, the first solution is x to the power r, the second solution is just obtained by multiplying the first solution by log x, right? So I will write that here. The first solution will be same, a naught plus a1x plus dash dash dash, and the second solution will be obtained by just multiplying the previous solution by log x, right? This is for the case when r1 is equal to r2 is equal to r, right? I will repeat that point, right? If you see this solution of this differential equation, you have to consider two cases separately. First, you should ignore the numerator, that is, consider the numerator equal to 1, or you can consider it equal to p naught, and this one also, you should consider the numerator as q naught only, right? Then this differential equation will closely resemble this equation, and you can see that its solution is given by x to the power r. So that's why I have written x to the power r, right? This is the first case. For the second case, you have to ignore the denominators, x and x square, right? In this case, this differential equation will be similar to the case we discussed in our last video, right? Where x naught is a regular singular point, where this px and this qx are analytic functions, right? And since we don't have any denominator here, that's why this is analytic, this is also analytic, and we hope that solution is obtained by power series method that works in our last video, right? That's why this should be the part of solution. This is just power series, right? That's why I multiplied the two cases. So this solution is actually the combination of two cases. First case, the last video. Second case, this Cauchy-Euler equation, right? And when we have distinct roots, this is the only solution, or should I write x to the power r1, and secondly I should write plus x to the power r2 and this series, right? Okay. So this is the explanation for this x to the power r, why we multiplied with x to the power r. Not only we can multiply with x to the power r, we have to multiply with log x also when we have repeated roots, right? r1 and r2 are equal. This is a explanation for this x to the power r, right? So now I will write a method how to solve a differential equation when we have a regular singular point. Method, right? So we are given the differential equation in this form, y double dash plus px y dash plus qx y equal to 0, right? I will call it equation number A, right? So step number 1, let we have the solution of this differential equation of this form, and that is a n x to the power n plus r, and n starts from 0 to infinity, and a naught is not equal to 0, and r is any real number, right? So this is the Frobenius series. We'll start with this Frobenius series, right? In second step, I will obtain y dash and y double dash by just differentiating them, and we'll plug those values in A, right? And plug them in A, right? Third step, I will equate the least powers of x, both sides, right, to get a quadratic equation, in R. It is called Indicial Equation, right? So the steps are pretty similar to that power series solution method. We just plug the values of derivatives and y in our original differential equation, and then we start comparing. First, I will compare the least powers of x, right? In that power series method, the least powers of x were constant terms, but here constant terms are generally not involved, right? The least power of x is generally, in most of the cases, x to the power r, right? But not always. So when we equate the least powers of x that are generally x to the power r in most of the examples, then I will get a quadratic equation in R. That is a very important point, and that equation is called Indicial Equation, right? Okay. I will solve this Indicial Equation to get obviously two values of R, R1 and R2, right? So solve it to get values R1 and R2, right? Okay, they may be distinct, they may be equal. That will be a separate case. First, I will write what we should do in step number 4. We should equate the coefficient of x to the power n plus r, okay, I should write this n plus r, I mean the highest visible coefficient, the highest visible power of x, right? So should I write x to the power n plus r, or x to the power n plus r plus 1, or x to the power n plus r plus 2? That depends on numerical, right? Any of these powers will work, right? So roughly we can say the highest visible power, right? However, the highest word should not be used because there is no highest power, because the range starts from 0 to infinity. So the highest power of x can be anything, right? So there is no highest. So we can compare any power, x to the power n plus r, x to the power n plus r plus 1, x to the power n plus r plus 2, whichever convenient, right? This will be discussed in numerical in detail, right? So any of these power will equate, and to get a recurrence relation. A recurrence relation is nothing but it is just a relationship between the nth term or n minus 1th term of these suffixes an, these subscript, these coefficients, sorry, an plus 1 in terms of an, right, or an plus 2 in terms of an, anything, a recurrence relation. Recurrence relation is also called as difference equation. That was a part of our syllabus. So to get a recurrence relation, n, I will write an roughly, an plus 2, an plus 1, it can be anything, right? Okay, then what we'll do, we will find a naught, a1, a2, etc. from this recurrence relation, from the recurrence relation, right? Generally a naught is not found, we find a1, a2 and so on, right? Because a naught is unknown. Sixth, after finding all of these coefficients, I will put those coefficients here. Actually this is in expanded version. I should write this as, if I put n equal to 0 here, I will get a naught x to the power r, and x to the power r can be taken common because x to the power r is not involved in summation. The summation is running from n equal to 0 to infinity. There is no point writing x to the power r inside summation. We can write that outside also, right? Because r is not the part of the range, n is the part of range. That's why x to the power r can be written outside. Then we'll be left with a n x to the power n, and that is just the power series, a naught plus a1x plus a2 x square and so on. Note that a naught is not equal to 0. I will write that here, is equal to where a naught is not equal to 0, right? Okay, so we can put these coefficients a1, a2 and so on in this power series, right? Substitute these ai's, all of these, in the solution, right? In y equal to x to the power r, a naught plus a1x and so on, right? Okay, so this is a kind of solution, but it is not the complete solution. It is still involving r. We have to put the values of r, r1 and r2 here in order to get the complete solution, right? So after this we have two cases actually. Case 1 when r1 and r2 are distinct roots, and case 2 when r1 and r2 are repeated roots. So I will write those cases here, put a partition here rather. So case A, after this 6th step, case A for 6th step, that is if r1 is not equal to r2, first thing is that, right? And important point is that r1 minus r2 is equal to a non-integer value. This is also important. First thing is that they should be distinct, but the difference should be a non-integer, right? I will explain this point later in our next video, right? Why this is taken. So then the solution is of the form, then we have two solutions. The first solution is denoted by y1, and that is just the solution obtained in step number 6, and you can see that you have r here, right? You will just replace this r by r1, right? That will give you the first solution y1, right? And the second solution will be just obtained from this y by replacing this r by r2, right? So we have two solutions at your hand, and the final solution will be given by the linear combination of these two solutions, c1y1 and c2y2 is the complete solution, right? Because we know that we are solving a second order differential equation. So if we have two linearly independent solutions, y1 and y2, then we should have the linear combination as a full solution, right? So this is case A, right? And case B. Case B, if R1 is equal to R2, means the roots are equal, right? Then the first solution y1 is given by putting R1 here. In place of R, you should put R1. You will get the first solution, right? But how to get the second solution, right? So again, we have to rely on this fact. This fact is that when we get repeated roots, in case of Cauchy-Euler equation, we can just obtain the second solution. See this closely. This is the first solution for repeated root, and see the second solution. The second solution can be obtained by just multiplying the first solution with log x. That's it, right? So what we'll do after finding this y1, we will just multiply this y1 with log x to get the second solution, right? This is just the replica of that Cauchy-Euler equation. That Cauchy-Euler equation is very important to understand the foundation of this Frobenius series method, at least for these two cases, right? These two cases can be completely understood by this beautiful simplest equation, right? And y2 can be obtained just by multiplying the already obtained solution y1 with log x. So this is a y2. Now I can write the full solution. Therefore, y equal to c1 y1 plus c2 y2 is complete solution, right? So this is it for these two cases of Frobenius series. We still have two more cases, but I will discuss those cases in next video. So I will take examples of these two cases one by one. Example number 1. Solve x square y double dash 2x square y double dash minus xy dash plus 1 minus xy equal to 0, right? About x not equal to 0, right? So generally this point is skipped in numericals, but if it is given, then you will take this point, but if it is not given, you always consider x equal to 0, right? So first I have to decide that whether power series solution is applicable here, or should we directly go to Frobenius series solution, right? First thing is that, so I should check the behavior of px and qx, the coefficients of y dash and y, and that whether they are analytic functions at x equal to 0 or they are non-analytic, right? So I will pick the px and qx first solution. Here px is minus x over 2x square, that will give me minus 1 over 2x, I think, right? And qx is 1 minus x over 2x square, right? You can see that both of these px and qx are non-analytic at x equal to 0. If you put x equal to 0 here and here, they will go to infinity, blow up to infinity, right? They are non-analytic at x not equal to 0, right? That's fine. But now I have to check what happens if I multiply it with x and multiply this with x square, right? But x multiplied with px will give you minus half, and x square multiplied with the qx will give you 1 minus x over 2. And you can see that both of these are polynomials. This is a constant polynomial, this is polynomial of 1 degree, and polynomials are always analytic, at x not equal to 0, right? So we can say that x not equal to 0 is a regular singular point. Therefore, x not equal to 0 is a regular singular point, right? Okay. Now we hope that our solution will be of this form, Frobenius series form. Power series solution will not work here. So let the solution for this equation be of this form. Y is equal to, should I write the expanded version or this version? I will write both. First I will write the summation version, a n x to the power n plus r, n starts from 0 to infinity. And should I write the expanded version? a naught plus a1x plus a2x square and so on. And you should not forget to mention this beautiful condition that a naught is not equal to 0. The explanation is still remaining. I will explain that why a naught is not equal to 0. This is very important. Okay, so this is your Frobenius series solution, and R is to be determined, right? Okay, and now I will differentiate this y once and twice. Then I will substitute those values here in my differential equation. I need y double dash, I need y dash, right? So first I will differentiate it once. Okay, that will give me, and be careful at this point. You are differentiating with respect to x, so that will produce summation a n plus r, right, and x to the power n plus r minus 1, right? And here the range is unaffected and was 0 and is still 0. Start from 0. That is different from that power series, right? This point is very important. When you differentiate a power series, that is of the form a naught plus a1x plus a2x square. The first term is a naught, constant term. When you differentiate it once, that a naught after differentiation goes to 0. The first term becomes a1 on differentiating it once. It means that the suffixes which was originally 0 in case of y, it becomes 1 in case of y dash. When you differentiate y, the first term becomes a1. It means that n should start from 1 in y dash, right, in case of power series. But when you have a series of this form, right, there is no chance to get a zero value after differentiation, because you can see that this is multiplied with this thing a naught x to the power r, and when you differentiate it, a naught will still be there in y dash. In fact, a naught will be everywhere in every derivative, right? So that's why there is no effect on the lower range of any derivative of y, as we have seen in the power series method, right? So this is again a new point, an important point. And differentiating it again, y double dash, and again the range will be unaffected on differentiation. That will be an n plus r n plus r minus 1 x to the power n plus r minus 2, right? Now I will plug those values here, right? Substitute in given differential equation, right? So see the first term is 2x square multiplied by y double dash. So I will multiply this with 2x square, and be careful at this point. 2 is a constant, so I will write that 2 here. Summation n equal to 0 to infinity. Again the same point. The range is unaffected by multiplying this any derivative of y with x to the power any number, right? I'm multiplying this with x square, but the range is still unaffected, but it was affected in case of power series, right? Okay, so a n plus r and n plus r minus 1 and x to the power n plus r minus 2 plus 2, because I multiplied this with x square, so that's why it will become n plus r only, right? The powers will add. So this is the first term. Now see the second term. Minus x times of y dash, and just multiply this with x, and it will become n plus r again. Okay, minus summation n equal to 0 to infinity an n plus r x to the power n plus r, right? On multiplying it with x, this minus 1 is cancelled, last term. But this last term is containing two terms. The first term is y, second term is minus xy. So I will write those two terms. First term is just y. Here's y. I will copy this y. I will add that here. Plus summation n equal to 0 to infinity a n x to the power n plus r. Now the last term, minus times xy. Minus times, you should just multiply this y by x. It will give you a n x to the power n plus r plus 1, yeah, equal to 0, right? So this is what we obtained after plugging these derivatives. Be careful at this point, right? And now we'll start the comparison, because we have got this relationship. Now I will start comparing the least powers of x, as I wrote here. Equate the least powers of x, and that's a very important point. What is the least power of x? From first term, the least power is obtained by putting n equal to 0, obviously. The least power will be x to the power r. As I said that generally in most of the examples, the least power is x to the power r, but not always. So the least power of x should be x to the power r. I will write that. Equate least powers of x, that is x to the power r in this example, right? So x to the power r term is contained in first summation. You can see that if you put n equal to 0, you will obtain x to the power r. So you should put n equal to 0 everywhere in the coefficient. You will get a naught, putting n equal to 0, okay, r, then r minus 1. In this term, you can see that if you put n equal to 0, you will get x to the power r. So that will give you minus a naught times r, right? Third term is also giving you x to the power r. You can see that if you put n equal to 0, that will give you plus a naught, right? Fourth term, yes. Fourth term cannot give you x to the power r. Why? Because you will put n equal to 0, you will get x to the power r plus 1. So there is no point, or there is no hope of getting x to the power r from the last summation, right? So I will write no term means 0 equal to 0, right? So we can say that the least powers of x may or may not be obtained from all the summation terms, right? In this example, the least power is obtained from only the first 3 summations, not from the fourth summation, right? Okay, fine. Now we'll take common. A naught should be taken common, and inside bracket I will be having r square minus 2r plus what happens, r square minus r, there was 2, we had 2 here, right? So 2r square, right, minus 2r minus r minus 3r, right, minus 3r plus 1 equal to 0, right? And now comes the explanation of this thing, why a naught is not equal to 0, right? Since we know that a naught is not equal to 0, since a naught is not equal to 0, so this factor should be 0 in order to get a 0 product, right? Therefore 2r square minus 3r plus 1 equal to 0, and this is called the Indicial Equation. So now you should understand the role of this a naught. If you take a naught equal to 0, then first thing is that you will not be having this quadratic equation, Indicial Equation. You must have Indicial Equation to get the values of r, right? If you choose a naught not equal to 0, in that case only you can put this equal to 0, right? And that's why the non-zero value is important for a naught. A naught should be equal to non-zero in order to get this Indicial Equation, right? Okay. I will solve this Indicial Equation here to get its roots. I think the factors will be 2r minus 1 and r minus 1. I'm correct. 2r square minus 2r minus r, yeah, okay, equal to 0. And this will give me two values of r. That is, one value is 1, another value is 1 by 2, right? And you can see that these roots are distinct roots. So at this point, you have to decide that whether you will follow case A or case B. This step is decisive step, right? You can see that I will write that step note here. The important point, a checkpoint, right? R1 is not equal to R2. First thing is that, right? And another important point is that their difference is a non-integer, right? And R1 minus R2 is actually 1 by 2, which is equal to a non-integer. So that confirms that we should follow case A, right? Okay. Now I will go to next step. I will compare the coefficient of x to the power n plus r, or x to the power n plus r plus 1, or x to the power n plus r plus 2, any coefficient of them, and that depends on the numerical. You can see that if you see the highest coefficient, however I should not use the word highest because the range is running to infinity, but the visible highest coefficient, the first in this summation, the coefficient is x to the power n plus r. It is also same, it is same, but it is highest of all of them, right? So I will compare the coefficient of x to the power n plus r plus 1 in this example, right? So equate or compare coefficients of x to the power n plus r plus 1, both sides, right? Okay. However, comparing x to the power n plus r will also give the same result, right? You can compare any coefficient, but the easiest is that the biggest coefficient appearing in the summation will give you the easy way, right? Okay, so x to the power n plus r plus 1, you just see the first term. Whether we will obtain this term from here, this is x to the power n plus r, we cannot say that this is the only last term. After, there are infinite number of terms. We can always obtain x to the power n plus r plus 1 from this summation. Why? Just put n equal to n plus 1. N equal to n plus 1. If you put n equal to n plus 1, then you will get n x to the power n plus 1 plus r, right? So I will trace the coefficient of x to the power n plus r plus 1 by considering n equal to n plus 1 from here, right? Okay, this will give you a n plus 1, n plus 1 plus r. I'm just scaling up n by 1, and this will give you n plus r. 1 is cancelled, right? And from here you will always obtain x to the power n plus r plus 1 by putting n equal to n plus 1, and that will give you, and again I forgot that 2, right? Okay, minus a n plus 1, n plus 1 plus r, and okay, fine. Third term, from here a n plus 1, a n plus 1, last term. Coefficient of x to the power n plus r plus 1 is minus n, that is fine, equal to 0, right? So at this point I can say that the coefficient of this thing, x to the power n plus r plus 1, or roughly I can say the highest visible power of x in the summation, right, is always obtained by all of summations, right? However, the least power of x is not obtained from all of the summations always, but the highest visible coefficient is always obtained from all of the terms, right? Now what I will do, I will try to obtain a recurrence relation. As I said there, a recurrence relation is a relationship between the terms an plus 1. So I will try to obtain the bigger coefficient. This is bigger, an plus 1. This is smaller, an. I will try to obtain an plus 1 in terms of an, right? So I will take that on the right hand side, and I will take common in this an plus 1 also, right? Or I should take an plus 1 common, and inside bracket I will be having, I should write that in tricky way, n plus r plus 1, should I write this way? Okay, and this is my n plus r, and this is again n plus r plus 1. Again I forgot that 2. Okay, 2 times minus, no, plus 1 equal to an, right? Now I will try to simplify it. However, this is a long polynomial, but I will try to simplify it in this way. Or an plus 1, watch the multiplication very closely. If I multiply this by 2n plus r, then this, that it will become twice of n plus r whole square. If I multiply this 2 with this 1, and that will become 2, and 2 multiplied with n plus r, right? Oh, I think I have made an error. I should have multiplied with the, okay, fine, that will be cancelled, fine. Okay, that will give you 2 times n plus r, right? And then taking this negative inside bracket, minus of n plus r, minus 1 plus 1 will be cancelled out. I think I am correct, an, right? And on simplification of this thing, I will have, or an plus 1, you will have 2 n plus r whole square plus n plus r, right, equal to an. And you can write an plus 1 equal to an divided by, you should take, what should be taken common? N plus r should be taken common, and inside bracket you will be having 2n plus 2r plus 1, right? So this is your an plus 1 in terms of an. This is called the recurrence relation. Recurrence relation, right? And let me call it equation number, what was that originally? And this is equation number 1, this is equation number 2, right? Now almost half of the job is done, right? So I will just plug n equal to 0, 1, 2, 3, and I will try to obtain those coefficients a1, a2, a3, and so on. I will just plug those coefficients here, and that's the solution, right? Before that, I have to rub that, and you should remember these cases. We are following case number 8 this time. The solution will be y1 and y2, which are obtained by just plugging r1 and r2 in place of r, right? Okay. So put n equal to 0, in that recurrence relation I will have a1 equal to a0 over r times 2r plus 1, right? Then put n equal to 1, I will get a2 equal to a1 divided by r plus 1 and 2r plus 3. And since I already have a1, I will substitute it here. That will give me r plus 1 r 2r plus 3 2r plus 1, right? And putting n equal to 2, I will get a3 equal to a2 divided by r plus 2 and 2r plus 5, right? Yes. And substituting the value of a2 from here, I will get a0 over r plus 2 r plus 1 r 2r plus 5 2r plus 3 and 2r plus 1. I think these coefficients are sufficient. I will plug those coefficients in my solution A, right? So put these AIs in equation number 1, and that will give me y is equal to x to the power r is outside. It is always convenient to substitute your a's in this expanded form, not in this summation. This summation is useful for getting derivatives and plugging those values here, but after getting all the coefficients, we should plug them in this expanded version. That's why I wrote both the versions, right? So y is equal to x to the power r, the value of a0 is not known to me, a0 is a0, right? I was able to find a1 in terms of a0, that is x0 over r times 2r plus 1, and we have x here. Then a2 was actually a0 times divided by r plus 1r 2r plus 3 and 2r plus 1, and we have x square here, right? We can write one more terms. I will stop here, plus dash dash. I'm not writing this term, right? Okay, and I should take a0 common in all of these two terms, right? If I take a0 common, that a0 will appear here, and okay, that will become 1, and this will also become 1 over this thing, right? You can see that a0 is present in the answer, and that's again this fact, a0 is not equal to 0. If a0 equal to 0, then we will get a 0 solution, y equal to 0, and 0 solution are of no importance, of no interest, right? Okay. So this is our solution, but this is not full solution. It is still involving the variable r. We have to get rid of this r, and we also know that r is actually equal to 1.5. So I will just plug those values here, right? So I will obtain the two solutions from here, and the first solution that is denoted by y1, and that is just the value of y, and replacing r by that first value. What is that? 1, right? So I'll plug 1 here in place of r. I will get a0 times x 1 plus x over, and this will become 3, plus x square over, this will become r equal to 1, 1 2 5 3 30, and so on, right? So this is my first solution, and to obtain second solution, y2 equal to y at r equal to second value is half, right? Okay, I will plug half here. I will get a0 square root of x, because x to the power half, right? And it will become 1 plus x over, putting half here, I will get half 1 plus 1 2 and 1, okay, 1 plus x square over, putting half here, it will become 3 by 2, become 1 by 2, and it will become 4, I think. It will become 3, right? No, 2, yeah, and it will become 6, and so on. So this is my second solution, right? So now I have got two linearly independent solutions. I claim that they are linearly independent. You can see that linearly independent solutions means if you have two solutions, y1 and y2, they are linearly independent, because if you take their ratio, that should be a non-constant, right? Then we say that the solutions are linearly independent. You can see that the ratio is a non-constant. Obviously a0 will be cancelled out. You will have some function, right? Therefore, the final solution is y is equal to c1 times y1 plus c2 times y2, right? Or y is equal to, when you multiply your y1, this thing, with c1, then c1 and a naught will be a new constant, product constant, and I'm replacing that c1 times a naught by a new constant, capital A, right? And after that, this x by 3 plus x square by 30 and so on, right? And c2 multiplied with y2, when you multiply your c2 with this y2, that c2 multiplied by a naught will be replaced by new constant b root x 1 plus x square by 6 and so on. I should mention here where I replace this a by c1 times a naught, and I wrote b in place of a naught times c2, right? So this is the full solution, is solution. Okay, so this was an example which was having two distinct roots differing by a non-integer value. Now I will take another example in which I will be having equal roots, right? Example number 2, solve xy double dash plus y dash minus y equal to 0, right? So about the point x equal to 0, that is understood if it is not written. Okay, so first checking the behavior of coefficients, px is 1 over x and qx is minus 1 over x, right? You can see that both of these coefficients are non-analytic at x equal to 0, right? Are not analytic at x equal to 0. So x equal to 0 is not an ordinary point. So we cannot use power series method. But we see that x times px is equal to 1 and x square times qx is equal to minus of x. They both are analytic at x equal to 0 because they are polynomials. You can see that, right? Okay, so we can say that x equal to 0 is a regular singular point, right? So considering the solution of that Frobenius series type, that is summation a n x to the power n plus r, and n starts from 0 to infinity, and should I write this in expanded version also, x to the power r a naught plus a1x plus a2 x square and so on. And again, the important condition that a naught is not equal to 0, right? Now I need the first derivative and second derivative also, so I will differentiate it. And as we know that on differentiating a Frobenius series, the range is unaffected, so that will give you a n times n plus r x to the power n plus r minus 1, right? On differentiating it again, I will get summation n equal to 0 to infinity a n n plus r n plus r minus 1 x to the power n plus r minus 2, right? Okay, I will plug those values in my differential equation, right? And I will assume that this is my equation number 1. Substitute these derivatives in given differential equation, right? So x multiplied with y double dash, so I will multiply this second derivative with x, and that will reduce the power of x to n plus r minus 1, right? I will write that in the first term, summation n equal to 0, and again the range is unaffected by multiplying any derivative of y with any power of x in case of this Frobenius series, right? So a n n plus r minus 1 x to the power n plus r minus 1, right? Second term is y dash, so this is your y dash, summation n equal to 0 to infinity a n n plus r x to the power n plus r minus 1, right? And the third term is minus of y, so I will write this minus summation a n x to the power n plus r, and it starts from 0 to infinity equal to 0, right? So I've got an equation and now I will start comparing the coefficients of x, and first I will equate the least power of x, right? As we have seen in the last example, that least power of x was x to the power r, but that is not the case always. This time you can see that the least power of x, if you check all of these terms, right, if put n equal to 0, obviously if you put n equal to 0, you will get x to the power r minus 1. It indicates that this time x to the power r minus 1 is the least power, right? Same is the situation from here, right? Okay, so be careful at this point. It is not that always you will have x to the power r is the least power. Sometimes you have different case. Compare least powers of x, that is x to the power r minus 1 in this example, right? In order to get the indicial equation, you must compare the least power of x, otherwise you will not get an indicial equation. Okay, so x to the power r minus 1, as we can see that the least power is and x to the power r minus 1, right? And from the first summation, as I told earlier, that the least power may or may not be obtained from all of the summations. So this time only first two summation terms is giving the least power. The third term, from the third term, you cannot obtain this power, right? Okay. So from here, if you put n equal to 0, you will get x to the power r minus 1. So I will plug n equal to 0 everywhere. I will get a naught r minus 1. This is from the first term. Second term, plus put n equal to 0, you will get a naught r. Okay, fine. From third term, you cannot obtain x to the power r minus 1, because in order to achieve that goal, you have to put n equal to minus 1, but that is not allowed, right? So this term will give you nothing, 0, equal to 0, right? And now I will take common a naught, and inside bracket I will be having r square minus r plus r equal to 0. And yeah, that will, since you know that this is not 0, right, so this will be equal to 0, or r square equal to 0. As you already know that a naught is not equal to 0, and this is called the indicial equation, but this time it is giving you two equal roots, right? The roots are equal. So we'll go to case number 2. Okay, I will add that point. Note, this is kind of checkpoint, a point where you should decide which case should be followed. It is a decisive step, right? Equal roots, r1 equal to r2 equal to r equal to 0, right? Equal roots. So we'll follow case 2. Okay, so now I will compare the highest visible power of x, and if you see these terms, it appears that this is the highest visible power, x to the power n plus r. So equate coefficients of x to the power n plus r. So from here you can always obtain the highest visible power from each and every term, right? So if I replace n by n plus 1, yes, okay, then I will obtain the highest visible power, x to the power n plus a n plus 1, n plus 1 plus r. From here, n plus r, yeah, okay. From here you should always get x to the power n plus r by replacing n by n plus 1. So that will give you a n plus 1, n plus 1 plus r, right? And from this term, yes, you will get x to the power n plus r minus a n equal to 0. So this time the highest coefficient is obtained from all of the summations, right? Now we'll try to obtain the recurrence relation, that is just a relationship between the higher coefficient and the least coefficient. I should take n plus r plus 1 common. So if I take n plus 1 plus r common, I will have, I think it will become n plus r plus 1 whole square, yeah, whole square equal to a n, right? And this will give you a n plus 1 equal to a n divided by n plus r plus 1 whole square. This is the recurrence relation, right? And in this relation, I'll put values n equal to 0, 1, 2, 3 to obtain a1, a2, a3 and so on, right? Put n equal to 0 first, and if I put n equal to 0, I will get a1 equal to a naught over r plus 1 whole square, right? If I put n equal to 1, I will get a2 equal to a1 over r plus 2 whole square, and since I know the value of a1, I will use this value a0 over r plus 2 whole square r plus 1 whole square, right? So we are getting a definite pattern from these coefficients. Putting n equal to 2 one more time, I will get a3 equal to a2 divided by r plus 3 whole square, right? And you just use this value, that will give you a0 over r plus 3 whole square r plus 2 whole square r plus 1 whole square. I think these coefficients are sufficient. Now what I will do, I will plug these coefficients, plug these ai's in your solution, equation number 1, right, in this expanded form. That will give you y is equal to x to the power r is outside, and inside you will have a0, and a0 is present in each and every term. You see that a0. I should take that common rather. A0 times x to the power r. The first term is 1. Second term is a1 times x. This will become x over r plus 1 whole square. Second term will be x square over r plus 2 whole square r plus 1 whole square. Third term will be x cube over r plus 3 whole square r plus 2 whole square r plus 1 whole square, and so on, right? Now since I have got equal roots 0 0, so first solution can always be obtained by putting r equal to 0 directly, right? Therefore first solution, that is denoted by y1, and that is just the value of y at r equal to the first root r equal to 0. So if I put r equal to 0 here, I will get a0 1 plus x over 1 square, x square over 2 square dot 1 square, x cube over 3 square dot 2 square 1 square, and so on. This is the first solution, right? Now in order to obtain the second solution, which should be the linearly independent with this solution, I should multiply this with log x, right? This is the case number B. Okay. Second solution, y2 is just the multiple of first solution by this factor log x. So I should write log x here, log x, and this will be same, and so on, right? I'm not writing all the terms. Okay, now the linear combination of these two functions will be your final solution, c1 y1 plus c2 y2, right? So multiplying c1 with y1, that would do c1 times a0 outside the bracket, and I will replace that by capital A, right? And inside I will have a 1 over x over 1 square, x square over 2 square 1 square, and so on. And for second, c2 multiplied with y2, if you multiply the c2 with y2, you will get c2 times a0. Then produce capital B, and log x is still there, 1 plus x over 1 square, x square over 2 square 1 square, and so on. So this is your final solution, is complete solution, where we have made this assumption capital A was actually equal to c1 times a0, and capital B was actually equal to c2 times a0, right? So this is how a Frobenius series solution works when you have a regular singular point for a differential equation. And note that power series solution is just a special case of Frobenius series solution if you assume r equal to 0. See this series, if you assume r equal to 0, this will become a power series, right? Okay, so we can say that as in the last video we used power series, this Frobenius series is also applicable in those examples. This is the most general series where you can use, where you have x0 as an ordinary point, you can always use this series, right? Okay, and one more thing, this thing, what about this? What happens when we multiply this by x, px, and qx is multiplied with x square? Why they become analytic? It indicates that, and it also have some another name. I wrote that was weakly singular, right? It means that such functions px and qx, when you multiply that px by x minus x naught and multiply that qx by x minus x naught whole square, they are converted into an analytic function, right? Roughly you can say that by just merely multiplying them with a 1 degree polynomial x minus x naught and the qx with the 2nd degree polynomial x minus x naught whole square. It indicates that those px and qx are weakly singular function. It means that they have singularity at x equal to x naught, that is correct, right? But that singularity is not worse than the rational function 1 over x minus x naught and 1 over x minus x naught whole square, right? In complex analysis you call that poles of first order and second order. If you have a little bit knowledge of complex analysis, then a function like 1 over x minus x naught has a pole at x equal to x naught of order 1, and 1 over x minus x naught whole square has a pole at x equal to x naught of order 2. It means that to use this method, your px and qx must have a singularity at x equal to x naught, but not worse than the rational function 1 over x minus x naught and 1 over x minus x naught whole square. In that case, you can use this Frobenius series method, right? But in this video, we have discussed in only two cases: the cases when the roots are distinct and they differ by a non-integer value, and the second case when you have repeated roots, right? And again, the nature of the solution, if you see this solution, the solutions are very similar to that Cauchy-Euler homogeneous equation, because Cauchy-Euler homogeneous equation is the fundamental for this whole Frobenius series method, right? In the next video, we'll be discussing two more cases one by one, and that will be part of the next video. For this video, thanks.